All right, let's get started looking at our warm-up here. So the first one is, what are the 4 properties of water that make it so darn important? Adhesion, nope, not polarity. Adhesion and cohesion are the first one.
Transpiration.
Nope, that one goes in with adhesion and cohesion.
Evaporation.
Those two are there. Those two, hold on. The universal solvent, we'll do that. We'll put that one down because that one's definitely right. So it's a good solvent. What did you got, Spencer?
As less dense as it is solid.
Less dense as a solid, so we'll say, we'll just say that.
But I guess
High heat
technically that's
evaporation.
But the high heat of evaporation and the high heat of vaporization are both important for, or the specific heat are both important for what? Temperature regulation.
although technically I guess it being less dense as a solid is caused by the hydrogen bonds, which is adhesion and cohesion.
Right, well, that's what he said. These are the properties, these are emergent properties of water, right? So these are the 4 special properties of water, not what causes them. But they're going to be caused by the...
What causes the other though? It's like cohesion, the cohesion between the water molecules as temperature decreases causes the crystallization.
It's the that's less dense as a solid. It's not necessarily the cohesion that causes it. It's just the lattice structure formed of ice as it cools.
Isn't that because it forms hydrogen bonds with itself?
But hydrogen bonding is
Okay.
a different, it's kind of like a cause and these are the effects. Okay, and that's what we mean. So we want to see the effects of water. What are the 3 types of intermolecular forces? Let's go ahead and do them in order of inter. Which ones are those?
The ones between molecules.
Between molecules.
No, I know which ones, but I think.
No, I was just saying in general. So what are they? I want them in order, the strongest to the weakest.
Hydrogen.
So strongest,
Dipole.
And then those Van der Waals.
Van der Waals.
Brandon, why you don't even have your head on? It's not even on.
hydrogen bonding, dipole, dipole.
It's like too high. It's gonna come off.
Yes, sir.
So great.
Isn't hydrogen bonding a special kind of dipole?
It is, but it's considered to be the strongest type of it's a special type of intermolecular force. And van der Waals. And we can also call van der Waals what? London. Van der Waals is what they like to call it in biology. So Spencer is absolutely correct. He said that hydrogen bonding isn't that just a special type of dipole-dipole. It is a special type of dipole-dipole. Hydrogen bonding is going.
Super special.
Hydrogen bonding occurs in. We'll start with hydrogen. What type of molecules will hydrogen bonding occur in?
Nitrogen, chlorine, and oxygen.
Polar or nonpolar? Polar. Okay, and polar molecules with HF, HO, or HN. That's our hydrogen bonding. What about dipole-dipole? Dipole-dipole is going to be polar or nonpolar? Polar. And finally, let's put all my answers up in a little pile.
Finally, everything else.
Finally, yep, is going to be van der Waals.
Vander was one word. Oh,
I told you about
Mr.
Alpha
Vander.
Felix, Mr. Vander.
Sure. Wall.
And this is going to be polar or nonpolar?
I hear Vanderbilt.
Nonpolar. Also, it's going to be found in polar. So basically, it's safe to say it's going to be in all has it, right? They all have it.
Is this the same Vander who the college is named after?
Yeah. It's the one that Vanderbilt?
Yeah.
Yeah, yes, absolutely.
Really?
No.
Oh.
Brandon, we just said that
I
it's
am
not
tired
his name.
and I will not understand any.
Do you want to know what's sad?
Get any
We
joke.
just said that.
You know, speaking of misunderstanding things, Jacob went to class and he says, do you know what the Illuminati is?
Oh god.
And this one little boy came back, he's like, oh yeah, he's like, we eat there all the time. And he came back to me and goes, do you know that there's a restaurant called Illuminati? I'm like,
Yes.
what? He says, yeah, my friend says there's a restaurant named Illuminati. I'm like, Lou Malnati's?
Oh my goodness.
So it was just so cute because now they all think that the Illuminati is like a conspiracy about pizza. So
Yes.
It always has been. It's a
Beautiful.
triangle.
pizza is a triangle.
Oh my god.
Oh my-
Illuminati confirmed.
Wow.
Oh my god.
God, it's so obvious.
They're in second grade, so I guess it's allowed. Why is the behavior of ice as a solid so unique and important?
Because it floats.
Okay, that's a basic answer.
So it insulates
Basic
the
bitch.
lake underneath it, and so that prevents everything from freezing
It-
underneath it.
It floats, so it insulates.
Yeah.
So we've got it insulates bodies of water during winter.
Winner.
That's one thing.
Oh shit.
What else does it do?
Reflects
The
radiation from the sun, so we're not microwaved alive.
ice caps reflect
The sun doesn't really produce many microbes.
sunlight
We have the
to help regulate Earth temp. What else?
Doesn't cause complete freezing of bodies of water. Means that bodies of water don't completely freeze.
That's what we just said right there in the first one.
The ice stays awesomely on the top when you drink iced tea.
I see now. Iced tea. Now, what about
That was a strange man.
it allows for the nutrient cycling? Remember what we said? We said if this is my body of water, what happens just like in your house? The cold
Oh, yeah.
is going to go down and the
Worm's gonna-
warm is going to go up. And it's going to keep doing that. And as it starts to turn into cold, it's going to start going down. So you end up with this upwelling effect. And so the nutrients that were up here, so here's my nutrients. What kind of nutrients? I don't know, things like phosphorus, nitrogen, dissolved oxygen. I know you like dissolved oxygen, right? These things are all going to be pulled down with this cold water, and it's going to distribute it down to the bottom. And there's water over here where it does, instead of having the dots of dissolved oxygen, it's got emptiness. Oh, boo-hoo, we're sad. It's going to go up to the top, and it's going to be able to get replenished, essentially, with nutrients. And then it's going to be able to start spreading the stuff, spreading the love, okay? So that upwelling, it's a very important process. It allows for those ecosystems to survive. Describe how plants get nutrients all the way to the top.
So the roots
That's the word, but that doesn't that's not describing it.
Using the force of cohesion and adhesion, water is able to
The
climb up the roots of the tree as well as propel itself through its own attractions to itself to get to the top of the tree and spread through it.
So it's the process of transpiration. It uses both adhesion, it uses cohesion. How does it use adhesion?
So it attaches, it can climb up the tree,
Up what part?
the roots.
Attraction to inside. It's not the inside of the tree itself, but it's the inside of what? The vasculature of it. So the xylem and the phloem. Let's make some space. Inside tree or plant vasculature. And you said it essentially pulls or propels upward by the constant making and breaking of those bonds, right?
Don't do it. Don't do it. Don't do it. Don't do it. Don't do it.
What about the cohesion? How does the cohesion work?
Sorry, they told me.
I think the door was here.
Sorry, they told me not to do it.
That's okay.
How does the cohesion work? Oh, I'm in the middle of class right now. I'm recording it, so go ahead. You'll be on the recording. What's your question?
Okay, I was just wanna ask for that, like the percentage composition. Does it mean like for what you gave us?
No,
or-
what you got.
Okay,
Yes.
That was it?
that's it.
That's it.
Did you get your jacket back? Your sweatshirt?
Oh, where is it?
Hesper has it. You left it in here, A block. Hesper took it E block to give to you. Uh-huh.
Okay, so make sure it's the theoretical.
Which one did you have?
B.
So how does cohesion help? So as the water molecules are attracted to each other, it climbs up the plant. But why does it go up?
Wait, cohesion?
Due to
Oh, each other. Okay.
due to what?
If the evaporating water leaving, pulling it, but.
To the evaporating. Where's the water evaporating from? From the stoma.
Wait, so as H2O attracted to each other, climbs up.
Wait, and this is the same thing as drinking
So isn't H2O climbing up the plant due to evaporation, not cohesion? Or
No, cohesion. The evaporation helps pull it up, but the water molecules they stick to.
oh, and then that's why they
That's
stay
why the
together
whole
while it's being
they
pulled
right.
up.
So as one leaves, the other one's replacing it because they're attracted to each other. So as one leaves by evaporation, another one takes its place because of their attractive forces to each other. So we have to now take a look at carbon. All life is built on carbon. You should know that about 72% of your cells is water. About 25% is carbon-based compounds like carbs, lipids, proteins, and nucleic acids. And then the other 3% are going to be your trace ions.
So do we get into the 4 major macromolecules?
That's what this
Today?
unit's all. Well, we'll touch on them, but we won't get into them much. Remember the chemistry, organic chemistry study of carbon-based compounds. It's got to have what? Must have carbon and hydrogen, and in biology. In bio, it's got to have CHO usually. Yep. Carbon atoms, they're considered versatile building blocks. Carbon is she's a skank, man. She'll bond with anything. It's got four valence. No, fluorine's the man, and it's different when you're a man, but when you're a girl,
True.
people talk, right? So fluorine might be the man and wants to bond with everything because he can, but carbon can bond with 4 different things at once.
Dang.
Carbon is a party girl, okay? So carbon has 4 valence electrons. How many does it want to be stable? 8. 8 is great, the octet rule. So in order to achieve its stable octet, it can bond with 4 other things. And this is a special property of carbon, and we say that it is, give her a pretty color, because it is tetravalent. Means that it can form bonds with its 4 valent electrons. It is
Can't other things do that
tetravalent. Anything that's in that same group. But carbon does it most readily. So if you go back and you think about the structure, if you do like a little Lewis structure for carbon, I'm going to put my carbon in the center. Carbon has 6 protons, right? So 6 protons, which means that it's got 6 electrons. So I'm going to have 1s2, 2s4, 2s2, 2p2. So here's my carbon, like that. then I'm going to end up with so we've got space for other ones here, we've got 2 here. Because we know that S&P hybridization, really we're going to end up forming 4 all the way around.
It's like halfway.
Yeah, because of the S and the P orbital, the S&P hybridization. That's why you end up with things that look like this. Just a simple ball and stick model there. It's tetrahedral. That's just methane, it's tetrahedral. You should know the structure of methane. Methane is the most simple hydrocarbon. So you should know that CH4, yes, but you should also be able to draw out a Lewis structure for it. You should also be able to identify its Vesper structure. So we just said it's going to be tetrahedral. If I ask you to draw a Lewis diagram of it, you should have C like that. So we can then take this carbon, because carbon is so happy to form bonds readily, we can let carbon bond in many different ways. So if you look at our carbon here,
How do you name these molecules?
Just do it.
Bob, no, there's a special way to do it. Like,
Do it.
you didn't, no,
Been learning now.
no, you don't have to learn now. You just have to understand that carbon, because it can form 4 bonds all the way around, that carbon readily bonds with things. It most readily is going to bond with, carbon's most readily going to bond with H, O, N, P, S, and of course, itself. Okay, it's always, those are the ones that it likes to bond with the most. If you look at these things, you notice that the carbon here, it can form single bonds right there, or it can form double bonds like right there.
Don't do it.
So if we look at hydrocarbons, it's both carbon and hydrogen. It is non-polar. Because it's non-polar, you know that it's not soluble in water, which means it is hydrophobic. These tend to be very stable molecules because there's not a lot of attraction between them, which means that they're going to be gases at room temperature. If there were a lot of attractive forces between them, the kinetic energy would slow down due to the difference or the greater pull of attraction between the molecules, and you'd end up with liquids or solids at room temperature. So how can we differentiate? If we're just making a bunch of things out of hydrogen and carbon, how are we going to make them different? Well, hydrocarbons can differ in 4 major ways. The first one is length, meaning how many carbons it has. So these is going to be the 4 ways to differentiate hydrocarbons. The first way is going to be their length. This just means add more carbon. How many carbons did methane have? 1. So methane is 1. 2 carbons is ethane. 3 carbons is propane and propane accessories. Do you know what 4 carbons is?
Yeah.
Butane.
Oh, it says right there.
Well, I don't know. I just knew that.
What's 5 carbons, guys?
Methane, ethane, butane.
Pentane.
5 is pentane.
For real?
Yeah.
Dang. Look at that. Look at those gases.
The second way you can do it, that we can change things, is via branching. Well, what does that mean? Instead of it being in a straight line like it is in the first one, we can, instead of having all of these hydrogen or carbons in a line like we do here, we're going to have one stacked on top of each other.
So it changes the shape.
It changes the shape, and if we change the shape, what does that do? Changes the function, absolutely. So branching is another way we can differ in our hydrocarbons. So if you look here, this is butane, in its normal form. But if we branch it out, it still has 1, 2, 3, 4 carbons. So it's still a type of butane, but what type of butane in it? It's isobutane. So if you look here, butene, if it ends in ene, just to let you know, it lets me know that it's got a double bond somewhere in it, if it's an organic molecule. Okay? So here I have 1 butene. Why is it called 1 butene? Yeah. Like, why is it called 1 butene? Because where's my double bond here? At the first carbon. This is 2 butene. Why do you think it's called 2 butene?
The second carbon.
It's at the second carbon. So the next way I can do it is I can have double bonds. I could even have
Triple bond.
or triple bonds.
Oh, for
Yeah.
quadruple bond.
So the number of bonds. So if you look,
Carbon is tetravalent, it could connect 4 bonds to other carbon.
no.
But I'm saying it wouldn't, I'm not saying. it
What
would-
about like
I'm saying it wouldn't make
pentabonds and hexabonds?
No.
If it's a single bond, carbon have single bonds, double bonds, or triple bonds. As you go down,
You get shorter
that's right, bond length
and stronger.
decreases and bond strength increases.
But
The great way to think of that,
it's like those things.
it's like jump ropes. If I had like a cord or a rope in between you, right? If John and we had one jump rope and we're holding it in between us and we have it just folded, not folded at all, it's just one length. You and I we're far away because of the whole length of it. But what if we wanted to be closer? We could fold it in half. Now, if we folded it in half, it's going to be double the strength, right? But we're closer because we've shortened how far apart we are. What if we wanted to make it even stronger? We can fold it in thirds, and we'd be even closer because we've decreased the distance between us, but it's going to be even harder to break because now we've got more reinforcement on that. So bonds are a lot the same way. So as the number of bonds increases, the bond length decreases and bond strength
Are
increases.
these in red web, Michelle?
No. The final one, I'll put it up, I will, is we can form rings. One of the cool things about carbon-based structures is they don't mind being in ring shape. And remember, when we talk about our monosaccharides, we said that our monosaccharides are rings in water or aqueous environments. So it can form a ring structure. Because you can have hexane, which would just be a straight row this is just hexane.
I think you need to start somewhere.
That's hexane. Cyclohexane is literally when it's just in a circle. What? Go for it. So this brings us to this idea of isomers, molecules with the same formula but different shapes. Remember, shape dictates function, so different shape, different function. A great example are going to be your monosaccharides. What is the chemical formula for a monosaccharide? C6H12O6 every single time. That's going to be glucose, fructose, galactose.
So they all are the same formula but different structure?
Mm-hmm.
So how do we know if C6H12O6 is glucose, fructose, or galactose?
They'll tell you.
Oh, right.
But all three of those, they all have the same chemical formula, but they have different structures. But what they do is functionally different. So how does that go along with that idea of form dictate or structure dictating function? Well, structural differences are an important functional significance. So you have different amino acids. Alanine is an amino acid. Well, you can have L-alanine, which is used in proteins, but D-alanine isn't. This goes into different medications where you have L and D versions of it, where sometimes they have the same chemical formula, so like, oh, we can make this will be great, but they act very differently. They're called stereoisomers. They're kind of like mirror images of each other.
Chirality.
Yes, sir. So the example you have here is like L-DOPA is effective against Parkinson's disease, whereas D-DOPA doesn't do anything. So if I gave you a medication,
Like non-superimposable mirror image or something, where it's like they have two different, it's the same thing. They're just mirror images.
Non-translatable mirror images.
yes, yes.
Wasn't
So-
there a thing with that with like morning pills for like
Right here, morning sickness pills. The thalidomide, which was prescribed for morning sickness in the 50s and 60s, like, oh, you have morning sickness, here, take this pill, it's fine. Well,
Wasn't it like half of them? They didn't know which one was the right one, so they put half and half of both. It's like the body took the right one, and then like did some other.
because, the stereoisomer causes severe birth defects, and that's what ended up happening.
See, because the thing is, isn't there like, can we like still not distinguish
Some
between,
things.
like, to tell which one's like lasting, which one's ready, for each for molecules?
No, not necessarily. I mean, if you looked at it at the molecular level,
Well,
they
yeah,
can
but,
totally
like-
do that, because otherwise you'd have medications out there that completely don't work. You know, like the Parkinson's medication they make, they're using L-DOPA. They know they're using L-DOPA. There's no point to them making the D form. But this is like thalidomide is a great example of how structure dictates function. It's a stereoisomer where it caused severe birth defects. And the birth defects were that the kids were being born with no arms. They'd have little hands at the end of their shoulders.
What the flip?
That's like, there's this acne medication for girls. You have to sign something saying you can't have sex. My friend was on it.
Yep.
Wait, what?
Because people kept having like kids, but they come out like with birth defects.
With so they would.
It's Accutane.
Accutane.
Oh, it's not acne medication. I thought,
Accutane is an acne
yeah.
medication.
well, then why would? Aren't there other acne medications that are?
Yeah,
It's really strong.
it's very, very strong. It works really, really well, but it has severe birth defects. They usually, if you go on Accutane, they generally want you on birth control at the same time.
Yeah, but
Oh.
like if you're not on it.
So if you're
What about
on
that?
it, so if you're off it, like how long do you have to wait until? Like how
Again,
long do you
everybody's
wait for
body
it until, like, your
metabolizes
body-
differently. I would wait at least 2 months.
Yeah, that scared me.
Yeah.
I thought it was like for life.
What
Like
about-
they.
No. Well, you're not gonna have a birth defect, honey.
But like, does the same pill work on guys?
Accutane?
Yeah.
Yeah. But it's
Well, but
we're not
wouldn't it
worried about you
transfer-
being
wouldn't it
pregnant.
transfer over to like.
No, because that's only, remember, genetic mutations from the male are only carried in the gamete. So it's not going to affect the males. The female is growing the fetus, so every toxin that she puts in her body, the baby is exposed to. So it's metabolized differently in the baby as well. So the thing to think about is the diversity of molecules. Get out your pens and papers. These are the functional groups again.
Oh no.
No.
Oh no.
Okay?
Can we get that shit
You've
again?
got to know your functional groups.
Because we got that sheet for baby bio. We got that like one sheet.
No, you had to write it out of your book. It's in your book.
Oh, flick.
So you just write them down as you go. First one we're going to do is your hydroxyl group. So ethane, remember we said that ethane was just 2 carbons? What we're going to do is we're going to replace one of the hydrogens with a hydroxyl group. Remember the hydroxyl is OH. What this does is we take a nonpolar inner ethane and we make it polar. If we've made it polar, what does that do? It can dissolve in water. What else?
What are these called?
It has stronger intermolecular forces, so it becomes a liquid at room temperature as opposed to a gas at room temperature. The functional groups. Yes, dear.
So I remember we were talking about this in bio freshman year, and no, it was chemistry sophomore year. And I looked it up again. There was like hydrogen bonds do happen in carbon if carbon's bonded to a larger macromolecule that increases its electronegativity. So it's,
That's-
it's a special case.
But that's not one of the three main groups. There's not hydrogen bonding with the carbon. It's going to be hydrogen bonding usually with another functional group attached to the carbon. Okay, in biology, that's what you need to worry about.
So what is this what is this doing? If this is substituting other atoms or groups around the carbon with a hydroxyl group?
Hydroxyl group is just OH.
So it becomes polar.
Yes. So here are the hydroxyl groups, or the functional groups you have to know. Hydroxyl, carbonyl, carboxyl, amino. You guys all know that, plus phosphate, you all know. So the only one you really have to learn is the sulfahydryl.
Wait, you can't go back real quick.
Well, what's hydroxyl?
Oh wait.
OH. What's the carbonyl?
Carbonyl.
It is the CO group. Very good. What's the carboxyl?
COH.
COH. What is the amino group?
NH4.
NH3.
4, 3.
Because remember, we have to have one space for that carbon that it's attached to. What's the phosphate group?
PO4. No,
PO3. PO3. We've got to have a space for it to be attached to something else.
True.
And the sulfhydryl.
SOH. Nah. SOOH. SO4. SO3. SO3.
That's
what
sulfates.
That's sulfate. Sulfhydryl.
Yeah. So SOH. Nah.
SH.
SCOH. SH.
Not C. The C is not. These things are going to be linked to carbons. So these are all going
Wait, go
to.
back for
What is
the
it? What's the answer?
for the so it becomes polar and then
Right. And then it's also because it's going to have
just-
stronger attractive forces. So what's going to happen to it? It's going to go from things being a gas at room temperature to being a liquid because those intermolecular forces are going to be much stronger.
and then the third one was just biological.
It has biological importances. Why? Because water is a universal polar solvent. You're made primarily of water. You need your molecules to be polar.
So what is the?
We're going to get to it. Hold on, honey. Again, we want to do everything we can to increase the solubility in water because, like we just said, your body's made primarily of water. Your cells are made out of water. It's the solution in which all life takes place. You need to go ahead and modify these molecules so that you can use them in your. So if you look, where structure and function, why does this make a difference? Well, if you look, both male and an example would be between the male and female hormones. You have testosterone and estridiol. It's basically just estrogen.
Wait, so hydroxyl, carbonyl, carboxyl.
Hold on.
phosphate,
Well, yep, we're going to get to.
sulfoxyl.
I'm going
we're
to show you
getting
all of them, okay? So these two things have identical carbon skeletons. The attachment of the functional groups interacts with different targets in the body with different effects. The only difference among them is you've got a hydroxyl right here on the estrogen, and you've got a double bonded oxygen here on the testosterone.
So then why? So like, if people wanted
You put up
to,
the mass
um,
biology stuff, yeah. You did?
I did.
Put up the last guy.
It's up there now.
why do you need it? Why would people need
A
to
week.
make
How many are there?
There's only one. It's due in a week.
I thought it was for the entire unit.
No, I only put them up one at a time. When we start doing the next chapter, I put it up for chapter 2. When we finish chapter 3 or 2, then I'll put up chapter 3. Okay.
Isn't there a way like since there's so little difference, can't if like a girl wanted to become a guy, and, like they were like taking like the testosterone pills, couldn't they like take a pill or something that would just like bond with that hydrogen at the end and just take it off, or like vice versa, just add a hydrogen, like seek out that.
Now
thing.
you can't do it because you have other things that have those same functional groups, right? So if
but like, wouldn't that one be?
but you have hydroxyls on other things.
Lots
You
of
know,
other things.
yes. So if all it was seeking out was a hydroxyl, you'd have a problem. So what they do in that case is you just start taking more testosterone. Males and females, males have some estrogen, females have some testosterone. Everyone has both sex hormones in them. It's just the quantity you have is going to determine what secondary sex characteristics develop. So you have enough testosterone to where you don't have boobs, right?
I mean,
Well, not that I know of. and you're in class, so I'm assuming you don't have boobs because otherwise you'd never leave home, right?
I was
So-
so, binding.
Good for you. Well, but I'm saying, but you have more testosterone than estrogen, so you develop male secondary sex characteristics. So, but you have both groups have it. So that's not a viable way to do that. What they do is just bombard the body or increase the amount of testosterone that they would have to what would be considered a more masculine level.
But why do we need both? Why is it necessary to have both? Like, why does he need estrogen?
Because
There's touch my female side.
yeah, because everyone needs to enjoy a good Hallmark movie every now and then.
It's true.
There are certain processes it's important in, that's all, in the body.
That got me too much.
So here's your hydroxyl. OH, it makes things in alcohol. The end of the name will typically end in OL. You already know that one.
The OH, organic compounds with OH equal alcohols. Okay. So,
Alcohol. So right here,
wait.
OH just looks like that.
Dang, we know.
Have a great day, guys.
Wait, can you go back real quick? Go back.